Welcome to this session. So this is a third part of the Joule-Thomson coefficient. So already we discussed about the Joule-Thomson effect and Joule-Thomson coefficient derivation for the ideal gases. So this is the next part, third part. In this segment we are going to discuss about the derivation for the Joule-Thomson coefficient for the real gases. Right, now let us go to the derivation part.
Okay, this is the lengthy derivation. So you should know what are the various steps involved in this derivation, right? Already you know the value of mu Jt in terms of change in enthalpy with the pressure. So this derivation already we derived in the Joule-Thomson coefficient derivation for the ideal gases. Okay, you just check back that video tutorial. Now what is the final part we are going to derive, that is mu Jt equation for the real gas. This is the equation we require, that is 1 by Cp 2a RT minus B. So we are going to derive this equation only from this. Okay, right. Now what is the step number 1? In the step number 1 we are going to use the equation Gibbs-Helmholtz equation, G is equal to H minus Ts. From this equation we are going to derive the Maxwell relation. This relation we are going to derive. This is the step number 1. So we are going to use Gibbs-Helmholtz equation, and from that we are going to derive the Maxwell relation. Okay, right. Now the step number 2 is we are going to derive thermodynamic equation of state, that is this equation. We are going to derive this thermodynamic equation of state, this equation. For that we are going to use the enthalpy equation H is equal to E plus PV. So we are going to use this equation. So from here we are going to derive this equation. And note that in the derivation of thermodynamic equation of state we are going to use the Maxwell relation. Maxwell relation. See, this term, that is dV by dt at constant pressure, this term is present in the Maxwell relation. Similarly, that the same term is present here in the thermodynamic equation of state. So we are going to derive Maxwell relation first, and then we are going to derive the thermodynamic equation of state from the equation enthalpy equation H is equal to E plus PV. And finally, since we are going to find the mu Jt value for the real gases, so we need van der Waals equation. So from the van der Waals equation, that is P plus A by V squared into V minus B RT for 1 mole of van der Waals gas, real gas. From this equation we are going to find out what is this value. Okay, so this is the required format. This is the third step. Okay, and from this one we are going to find out the value of mu Jt. Okay, we are going to find out the value of mu Jt from this. So Maxwell relation is used to get the thermodynamic equation of state. Again, you see, from the thermodynamic equation of state we are going to use the van der Waals equation. The thermodynamic equation of state is used in the van der Waals equation. So these are the 3 steps involved in this derivation. So it's a lengthy derivation, so watch carefully step by step, and based on these 3 steps only I have given this tutorial. Okay, check this. Okay, now let us start with the Maxwell relation. Maxwell relation. Right. Before going into the Maxwell relation, you should know the Gibbs-Helmholtz equation, which is given as G is equal to H minus Ts, where you know what is H, what is T, what is S. H is the enthalpy, T is the temperature, and S is the entropy. Now what is G? G is the Gibbs free energy. So this equation, G is equal to H minus Ts, this equation is known as Gibbs-Helmholtz equation. Okay, so you know what is meant by free energy, right? You know you should differentiate between the internal energy from the free energy. Okay, right. Now already we discussed the value of S, that is entropy. The change in the entropy is given as dQ by T, right? The change in the entropy is given as change in the heat divided by the temperature. So TdS is equal to dQ. So you know this also. Okay, right. Now we are going to differentiate the Gibbs-Helmholtz equation. Just differentiate. So this equation, that is G is equal to H minus Ts, that equation becomes like this: dg, which is equal to dh minus tds minus sdt. Okay, right. Now we know that the value of H is equal to, that is enthalpy is equal to E plus PV. H is equal to E plus PV. Okay, already we discussed this equation in the heat capacity, that is CP/CV relation. In the heat capacity derivation, CP/CV relation, we discussed about this equation also. So you know that one. Now again differentiate this equation, because we are going to find the value of dH. So we are using this enthalpy equation, H is equal to E plus PV. So differentiate this equation again. On differentiating then equation 3, then the equation 3 becomes dH is equal to dE plus PdV plus VdP. Here you are having minus sign is present, so you are having minus TdS minus STT. Here you are having positive sign is present, so here plus PdV plus VdP. Right, now what? Now we are having the value of dH. Okay, now we are having the value of dH. So here you are having the value of dE. So you are going to find out the value of dE now. That can be taken from the first law, of thermodynamics. So you know this is the first law of thermodynamics. dE is equal to dQ minus PdV and dQ is equal to TdS. So this equation can be converted into like this. The dQ can be replaced by the TdS. So now you know the value of dE. Okay, now this dE value, the value of dE can be substituted into this equation. So what will happen now? So the equation 4 becomes dH is equal to TdS minus PdV. This term is introduced here, TdS minus PdV plus PdV plus VdP. So now you are having two terms with opposite signs, so just cancel the PdV terms. Now what is the simplified equation of the dH? So now we are having the value of dH is equal to TdS plus VdP. This is the equation number 5. Now what? Now we have find out the value of dH. So now we are going to substitute the value of dH, that is from equation 5, into equation 2. Okay, and we are going to find out finally what is the value of dG. Okay, right, now we need the equation 2 and the equation 5. Now let us go to the next one. Okay, now we are having the two equations, that is the value of dG as well as the value of dH. Right, now we are going to substitute the value of dH into the equation 2. From equation 5 we are going to substitute the value of dH into the equation 2, that is the dG equation. So then this is the substitution. Right, now there are two terms which are having opposite signs, that is TdS plus TdS and minus TdS. So let us cancel the terms. Now let us simplify the equation. So now after the substitution, this is the final format of the value of dG, that is dG is equal to VdP minus STT. Note down, here you are having two variables in this equation, that is one is pressure dP and another one is the temperature. So you are having two variables, pressure and temperature, and two constants, volume and the entropy. Okay, right. So based on this equation 6 only, we are going to find out the Maxwell relation. Okay, now assume if the condition is isobaric, that is pressure is constant, assume that at a constant pressure. Now what about the equation 6 now? What about the equation 6 now? Since pressure is constant, so here this variable, this is the variable dP is the dP becomes 0. Okay, so now the equation 6 is reduced into dG is equal to minus SDT, because this term becomes 0, that is VdP term becomes 0. Similarly, we can assume that the dt becomes 0. That means what? If dt is equal to 0 means what? the process is isothermal. The process belongs to isothermal. So now assume if the process is assumed as isothermal, then the equation 6 is reduced into dg is equal to vdp. So from 6 you are getting two equations at two different conditions. One is isobaric and another one is isothermal. Right. Now compare equation 7 and 8 again. So equation 6 is reduced into, equation 7 is reduced into like this, that is dg, this equation is rearranged, dg by dt at a constant pressure, which is equal to minus s. This is equation number 9, that is obtained from equation 7. Similarly, one more equation can be obtained from equation 8, that is dg by dp at a constant temperature, which is equal to v. So equation 8 can be rearranged into equation 10. So this is the base for the Maxwell relation. These two equations, that is equation 9 and equation 10, going to give the Maxwell relation. Now let us see how to derive the final part of the Maxwell relation from equation 9 and equation 10. Okay, now we got two equations. Now we are going to differentiate equation 9 with respect to pressure at a constant temperature. That is what we are doing. We are going to differentiate equation 9 in this condition. That is the condition maintained at equation 10. Okay, so differentiate equation 9 with respect to pressure like this. That is the condition maintained at the equation 10 at a constant temperature. Similarly, the equation 10 can be differentiated with respect to temperature at a constant pressure. That means we are going to differentiate equation 10, the condition that is maintained at equation 9. So we are going to differentiate equation 10 with respect to temperature at a constant pressure, whereas equation 9 is differentiated with respect to pressure at a constant temperature. Okay, so this condition is used to differentiate the equation 9, whereas this condition is used to differentiate equation 10. Right, now what is the result? So if you are differentiating equation 9 with respect to pressure at a constant temperature, then this is the result. So you are having a second derivative is obtained, that is dou square g divided by dt into dp, which is equal to minus dou s divided by dou p at a constant temperature. This is the equation that is obtained from equation 9. Okay. Similarly, if you are taking equation 10, differentiating equation 10 with respect to temperature, that is under this condition, under the condition of equation 9, then this is the equation we are obtaining. Okay, so here what is the result? So here the V becomes dou V divided by dou T at the constant pressure. So we are getting two equations, equation 11 and equation 12. Now, according to Euler's theorem, since G belongs to a state function, you know what is meant by a state function and what is meant by a path function. Since G belongs to a state function, and as per the Euler's theorem or Schwarz theorem, whatever may be, you can take the left hand side of the equation 11 is equal to the LHS of equation 12. So here you are having the denominator, look the denominator side, dt into dp. Here you are having dp into dt. So as per the Euler's theorem, since G belongs to the state function, so the right hand sides of the equation, that is RHS of the equation 11 and 12 are equal. So now what? The value of the Maxwell relation is written like this. So this term is equal to this. Okay. So the negative sign is taken the other hand side, the right hand side. So you are having the final format, that is ds divided by dp at a constant temperature, that is isothermal condition, which is equal to minus dv by dt at constant pressure. So this is the Maxwell relation. This is the Maxwell relation. This Maxwell relation is going to be used to derive the thermodynamic equation of state. Okay, so this is the condition. From this we are going to the next part. Now let us see the thermodynamic equation of state. Right? You know the enthalpy equation, H is equal to E plus PV. Again we are starting from the enthalpy equation, H is equal to E plus PV, and on differentiation, dH is equal to dE plus PdV plus VdP. So just now we have seen this part, isn't it? And the value of ds, that is TdS is equal to dQ, and from first law we know the value of dE is equal to TdS minus PdV. So substitute the value of dE from first law equation into the dH equation. So now this is the equation we got after the substitution of the value of dE. Okay, now again cancelling the terms, PdV terms, because they are having opposite sign, so you are having this equation. So already just now we derived this value of dH. The first part is we derived this equation, that is in the derivation of the Maxwell relation we used this equation, isn't it? So already we derived the equation 5. Right now the important thing is you should remember what is the value of mu j t in terms of dH. What is the value of mu j t in terms of dH? So this is the equation. Mu j t is equal to minus 1 by Cp dH divided by dP at a constant temperature. So this is the value, right? This is the value. Now we are going to find out the value of dH by dP at a constant temperature in the mu j t equation. So we are going to find out this value. This part we are going to find out. So now we are, you know what is the value of dH. So now we are going to divide equation 5 by dP at a constant temperature. What is the reason for doing this? What is the reason for doing the division by dP at a constant temperature? Because just refer the mu j t equation. Just to go to the mu j t equation. Here we have done the term is like that, isn't it? The value of mu j t, it contains a term dH by dP. Now we are having the dH equation. So this is the equation that is used in the Maxwell relation derivation. So now divide the equation 5 in this condition, the condition that is present in the equation, that is mu j t equation. Okay. Now what? After dividing equation 5 with respect to dP at a constant temperature, then this is the equation number 13. Okay. Now what? The dP term becomes 1. This where dP divided by dP becomes 1. So now we are having equation number 13. So from this we are going to get the final format of the thermodynamic equation of state. As already I told, this is a lengthy part. So just follow the steps carefully one by one. Then only you can go to the final part and you can understand the concept easily. Okay. Okay, now we are having the equation 13. What is the reason for getting this equation? Because you should remember in the mu j t equation we are having this term, that is dH by dP at a constant temperature, that is under isothermal condition we are obtaining the value of dH by dP at a constant temperature. That term is present in the mu j t equation. So we are going to find the solution for this equation. Now one more thing is, in the equation 13 we are having ds by dP term at a constant temperature, ds by dP at a constant temperature. This part we derived from the Maxwell relation, that is the ds by dP at a constant temperature. The value of ds by dP at a constant temperature we already obtained from the Maxwell's relation. What is the Maxwell relation? The ds by dP at a constant temperature, which is equal to minus dV by dt at a constant pressure. So now what? We are going to substitute the value of ds by dP, that is at a constant temperature. This value is going to be substituted in the equation number 13. Okay. Now substitute this value in the equation 13, that is the Maxwell relation value is substituted in the equation 13. Then the equation becomes, that is equation 13 becomes dH by dP at a constant temperature. Here we are having a minus sign is present, remember. So minus dt into dV by dt at a constant, this term is present like that, plus V. So you are having equation number 14 now. And finally, and of course this is the one form of the thermodynamic equation of state, because we are our main aim is to get the thermodynamic equation of state. So this is one form of the thermodynamic equation of state. So we derived Maxwell relation, and then we derived the one form of the thermodynamic equation of state. Now finally we are having the value of dH by dP at a constant temperature. So this term should be substituted into the mu J/T equation. So substitute equation 14, that is this term, into equation mu J/T equation. Okay, right? That is, substitute the thermodynamic equation of state into the mu J/T equation. So this is the substitution. Just I substituted the value like that. Okay. Now the minus terms are multiplied, and finally, what is the value of mu J/T? This is the final format. So the mu J/T is equal to 1 by Cp T into dV by dt at constant pressure minus V. Okay, so this is the equation number 15. So this is the value of mu J/T again. This is the value of mu J/T again, derived based on the thermodynamic equation of state. Okay, now we are going to find out the mu J/T value for the real gases. That is the final part. Okay, now coming to the van der Waals equation. You know the van der Waals equation, P plus A by V square into V minus B, which is equal to RT. This is for van der Waals equation for the real gases, isn't it? This equation is written for 1 mole of the gas. So here you know the value of P is the pressure, and V is the volume, R is the gas constant, 8.314 joules per Kelvin per mole, and T is the temperature. Okay, and what is A? A is the pressure correction factor or van der Waals constant. See, the A is associated with the P, the term P, pressure term. What is B? B is also a correction factor. That is the van der Waals constant. This is associated with the volume. So B is the volume correction factor and A is the correction factor for the pressure term. Now, rearrange this van der Waals equation. Just multiply the first term with the second term. Then what you got? So just multiply this term with this term. That's all. So this is the format. This is the equation after multiplication. Now, the term in this equation, the term A into B divided by B squared, this term is very, very small when you are comparing with the other terms, because you know the value of V, that is volume, that is the volume of the gas occupying at standard temperature pressure STP condition, is 22.4 liters for 1 mole, because we are deriving the equation for 1 mole. The value of V is equal to 22.4. Okay, 22.4 liters, 22.4 liters, the value of V at the STP. Now, for example, if you are taking hydrogen as an example, the value of A is 0.2453 bar liter square mole to the power minus 2. See, here we are having a pressure term because A is associated with the pressure. So the value of A is equal to 0.2453 bar liter square mole to the power minus 2, whereas the value of B is 0.0265 liters per mole. Okay. Now, what is the value of V? 22.4 liters. What is the value of V squared? 501.76 liters squared per mole. Again, it is also liters squared per mole. 501.76 liters squared per mole. So compare now the value of A into B. Suppose if you are multiplying A into B, the value still will still lowered, isn't it? So the value the term AB by V squared, this term is very, very small when you are comparing with the other terms. So in the forthcoming equations, we are going to neglect this term. We are going to eliminate this term because the reason is the value of AB is very small when you are comparing with the term V squared. So the denominator we are having the V squared. So we can neglect it. Right now, after removing the term AB by V squared, the equation becomes like this. Okay, right. Then just a simple rearrangement. Just a simple rearrangement. We are taking these two terms in the right hand side, right? That is right hand side. So this equation becomes PV is equal to RT minus A by V. Here you are having a minus term and plus BB. Okay. Now finally one more rearrangement. This term is rearranged again. That is V is equal to in terms of V. Okay. Or we can just simply divide this equation both sides by the pressure term, P term, pressure term. Okay. So what is the value now? V is equal to RT by P minus A divided by P into V. Here you are having P into V plus B. So this becomes B. Okay. So now we are having the value of V. Right. And one more assumption we are going to give here is, at very low pressure any real gas can behave ideally. At very low pressure any real gas can behave ideally. So you know the ideal gas equation, PV is equal to RT. So wherever the term PV is present under low pressure, very low pressure, we can replace it by RT. So in this equation we are having the PV term is present, so that PV term is replaced by RT. That is the only change done in this equation. So V is equal to RT by P minus A by RT plus B. Okay. So this is the assumption we are doing here. This is the assumption we have done here. Okay. So remember, this is the assumption, because at low pressure only this concept can be, that is PV is equal to RT, can be applied for the real gases. So the assumption we have made is PV is equal to RT. Okay, now we got the value of V. Value of V, that is this equation is obtained from the van der Waals equation. So this equation is obtained from the van der Waals equation. Now you should remember again the value of mu Jt. Value of mu Jt, that is the mu Jt in terms of thermodynamic equation of state. So here you can see the term dV by dt at constant pressure. This term is present in the mu Jt equation. Okay, this is the equation number 15. Already we derived the mu Jt in terms of thermodynamic equation of state. So now we are going to find out the value of dV by dt at constant pressure. This term we are going to find out. So from van der Waals equation we got the value of V. So we are going to derive this term from equation 16, that is dV by dt at a constant pressure. This term is present in the equation number 15. This term should be obtained from the equation number 16. Okay, so differentiate again equation 16 with respect to temperature at a constant pressure. Again, what is the reason for doing this differentiation? What is the reason for doing this differentiation with respect to temperature at a constant pressure? Because again, look, the mu Jt equation derived in terms of thermodynamic equation of state. Okay, so now we are going to convert equation 16 in this format, that is the dV by dt at a constant pressure. So equation 16 is differentiated with respect to temperature at constant pressure. Again, remember, because in this format we are going to look this format, just look this format equation, look the equation number 15. So in this format we are going to convert equation number 16. Right now, after differentiating, what is the value? dV by dt at a constant pressure. This value, this equation is differentiated with respect to temperature at a constant pressure. So here this the value of temperature, this value becomes 1, and A by RT, this value becomes A by RT square. Reason is because the reason is 1 by T into dt. So it's nothing but this is the format. So what is the solution for this equation? So this is the one. This is the one, minus T to the power minus 2. Okay. So or we can write minus 1 by T square. So what is the solution for this one? 1 by T. This term is nothing but minus 1 by T squared. So A by RT, this term becomes A by RT square. Since B is a constant, then that value becomes 0. So equation 16 on differentiation with respect to temperature at constant pressure yields equation number 17. Why we are doing this differentiation? Because the mu j_t term, in the mu j_t equation, we are having the dv by dt term is present. Look the equation number 15. So in order to solve this part, we are having the differentiation. Okay, we have done the differentiation. Okay, right. I think this will be clear because we are doing so many assumptions and so many differentiations. So you may get confused. So follow the steps. What is the reason for doing the differentiation? You should remember in each and every steps we are doing the differentiation because it is a part of the previous one. Okay, right. Now rearrange the equation number 16, not 17. Note that equation number 16 again, not 17. Remember this. Okay, right. Now if you are rearranging the equation number 16 in terms of RT by P, okay, so this is the thing, RT by P is present here, so V minus B, so this B term is taken into the left hand side, and the A by RT, this term is having a negative sign, so that becomes plus. So RT by P, we are rearranging the equation 16 again in terms of RT by P because we are going to find this term. That's the reason. R by P term we are going to find out. Equation 17, there is one term that is R by P. We are going to find this term. So we are again rearranging the equation 16. That's the reason. Okay. Now as usual, what is the value of R by P? What is the value of R by P? So R by P nothing but divide by temperature in both sides of this equation. Divide both sides of this equation by the temperature term, T term. So you are getting R by P term. Okay, so now we are going to substitute this in the equation number 17. So again, remember the crucial step, the important step is again we are rearranging the equation 16 and we are getting the value of R by P from equation 16 only, not from 17, right? So R by P term is equal to V minus B divided by temperature and A by RT squared, right? So equation 18 is obtained from this one, equation 16 itself. Okay, now we are having the R by P term. Now substitute the value of R by P, this value, the value of R by P should be substituted in the equation number 17 in this part. R by P should be substituted. So now what? The value of R by P from equation 18 is substituted into equation 17. So dV by dt at a constant pressure, which is equal to V minus B this term. Actually we have taken this term, isn't it? This equation 18 we are having this term. This term is written here. V minus B, this term is taken out from the equation number 18. So this is the equation, this term is taken from the equation number 18. Okay, right. So already one more term is there, where in the equation 17 we are having this term is present. Remember, we are having the A by RT squared. This term is already present in the equation 17, so that is present there. So now we have substituted the value of R by P from equation 18 into equation 17. Okay, now finally you are having two terms, so just to sum up. So this equation becomes like this: dV by dt at a constant pressure, which is equal to V minus B T plus 2A by RT squared. This is equation number 19. Okay, so of course this equation is bit lengthy. The video is also a bit lengthy one, because each and every step is taken from the previous one. See, in this step we have derived equation 16 from the van der Waals equation. Then we got equation 17 based on the mu j_t equation. Again, the equation 17, the value of R by P term is taken from again equation 16 only. So each and every step is following a chain-like format. So remember, so here finally we got this format, that is equation 19 is the final format. and based on that we are going to find the value of mu gt. Again, this is not in the mu gt form, so this value should be substituted in the mu gt equation. Now we have derived the value of dV by dt at constant pressure. Okay, now we are going to substitute this term into the mu gt equation. Okay, that's the final part. Okay, now coming to the final segment, this is the last part of the derivation. We are going to find out the value of mu gt for the real gases, right? So now we got the value of dV by dt at a constant pressure from the van der Waals equation. Okay, what is the reason? Because we know the value of mu gt. This is the value of mu gt written in terms of van der Waals equation of state. So we are having this term T into dV divided by dt at a constant pressure minus V. So we derived this part dV by dt at a constant pressure. So check the equation number 19 and the equation number 15. Compare both. Now we are having this term dV by dt at constant pressure. This term is present in the equation 15, that is mu gt equation, which is derived in terms of thermodynamic equation of state. Okay, right, now we are going to multiply the equation 19 by temperature T on both sides. That is, equation 19 is multiplied by temperature. What is the reason? Look this equation, here you are having the value of T is present. Okay, so in order to get this format, we are multiplying equation 19 by temperature. Okay, right, so what is the value? So if you are multiplying equation 19, we are getting one more equation, that is T into dV divided by dt at a constant pressure. So here the value of T is removed. The denominator, there is no T terms, and here the equation final part is 2a by RT. So equation 20 we got. Okay, what is the reason? Because check this value T into dV by dt at a constant pressure. This term is present here, and one more term we should get, that is minus V. Okay, right. So now rearrange again the equation 20, because we are having the V term is here, and now what is the required format? T into dV dt into P minus V. So we are taking the V term from here, that is from the right hand side to left hand side. So now rearrange equation 10, that means take the V from here to in this part. Okay, now what is the final value? So T into dV dt minus B, so minus V. So the term minus V is taken in the left hand side. So this is the required format, isn't it? This is the format which is present in the mu gt equation derived from the thermodynamic equation of state. Okay, right, now so this is the format minus B, remaining things are like that. So you are having one more equation, that is equation number 21. Okay, so and now substitute the value of T into dV by dt at a constant pressure. This term, substitute this value into the mu gt equation, that is the equation number 15. So substitute the equation number 21 into equation 15 for which term? This term, for this term T into dV divided by dt at a constant pressure minus V. So what is the value now? So this is the final equation for the mu gt in terms of van der Waals constants, that is for the real gas. So mu gt is equal to 1 by Cp 2a by RT minus B, 2a by RT minus B. So this term is present. You just remember in the equation number 21 we are having this term. So this is the mu gt equation for the real gases. Remember, you are having the value of A, that is the van der Waals constant A, and van der Waals constant B is present. So this equation is valid for real gases, van der Waals gases. Okay, right. Right, now coming to the final part. So we got the value of mu gt, the mu gt equations we got. So this is the mu gt equation, 1 by Cp 2a by RT minus B. So it contains the value of A, that is the van der Waals constant A as well as the van der Waals constant B. Okay, so this equation can be applied to real gases. Here the Cp is constant. So here what are the values? This is the value of mu gt. Cp is constant. So the term 2a by RT and B decides the value of mu gt. You should know this term 2a by RT, the first term, and the second term B decides the value of the sign for the mu gt. And remember, already we know the value of mu gt is nothing but dt by dp at a constant enthalpy. That is change in the temperature divided by dp. So if dp is positive, then cooling occurs. Mu gt is also positive. dt is positive, mu gt is also positive. You just refer back for these equations, for this that is mu gt and the value of dt, cooling of the gas in terms of iso-enthalpic condition. So you just refer back for this change in the temperature with respect to mu gt. So now, based on the sign of mu gt, we can have the or we can say like this: the sign of mu gt can be decided by two factors, that is 2a by RT minus B. This is the first factor, and one more factor is B. So the value of the sign for the mu gt can be decided by the two terms. Since Cp is constant, heat capacity at a constant pressure, this is a constant. Okay, right. Now suppose if this one 2a by RT, the first term is less than B, then naturally mu gt becomes negative. So what will happen now? If mu gt is negative means what? dt is also negative, right? So if 2a by RT is less than B, then mu gt becomes negative. That means dt is negative. So if you are doing Joule-Thomson effect, then heating occurs. Instead of cooling, heating occurs. Mu gt is negative, then heating occurs in that gases. Okay, right. Now the reverse. Suppose if 2a by RT is greater than the value of B, then what will happen? The mu gt becomes positive. Mu gt becomes positive and dt becomes positive. Note that dt is also positive. So what is the impact? The cooling occurs. This is the required thing. This is the practically we need cooling, isn't it? So in order to cool the gas, the value of 2a by RT should be greater than the value of B. Then only the value of dt becomes positive and mu gt becomes positive. So mu gt, in order to get the positive mu gt value, in order to cool a gas, you should remember the value of 2a by RT should be greater than the value of B. And one more condition is there. Suppose if these two values, the term first term and the second term, if these two terms are equal, then what? Then mu gt becomes 0, isn't it? The mu gt becomes, because the whole term becomes 0. So what is that one? Already we discussed in the case of the ideal gas mu gt derivation. So if mu gt is equal to 0, what? Then there is no cooling, no heating. Neither cooling nor heating occurs during the Joule-Thomson effect. So that type of gas belongs to ideal gas. Okay, so for real gases, the value may be positive or negative. For ideal gases, the value will be 0. How to distinguish a gas which belongs to ideal or real? If the mu gt becomes 0, then the gas belongs to ideal. If the mu gt is positive or negative, then the gas belongs to real gas. Okay, right. So this is the significance of this equation. So in order to cool a gas, in order to liquefy a gas, during the liquefaction process, mainly you should remember that the value of mu gt should be positive. Okay, in order to make it positive, the value of 2a by RT should be greater than the value of B. Okay, right. And finally, based on this, a concept of inversion temperature, how to increase the value of 2a by RT, but through the temperature. Okay, because we can't change the value of A, we can't change the value of R, but we can change the value of T, value of temperature. Because in order to, because B constant, here you note that B constant, A is also constant, R is also constant. So only thing is T. So we can change the temperature. So in order to make the mu gt positive, we can adjust the value of T. We can reduce the value of T. So a concept of inversion temperature, that is Ti, is derived from this equation. The concept of Ti, inversion temperature. There is a spelling mistake, derived from this equation. The concept of inversion temperature is derived from this equation. So this is the MuJT derivation for the real gases. Okay, right. The next concept we are going to discuss about the inversion temperature concept, and that is the extension of this one.